In this video, we'll be discussing the alternating series test. So first, to define what an alternating series is, an alternating series is any series whose terms alternate between positive and negative. There's some different ways to write this. For instance, an alternating series can be written in the form -1 to the n plus 1, and then some other sequence terms, or -1 to the n bn. Pretty much any power that is on the -1 that changes is going to give you an alternating series test. So it could be an n plus 2, n plus 5. These are just two very common examples. So the alternating series test is going to be the test that we use to determine convergence of these alternating series. So let's say we have one of those alternating series. It will converge if both of the following conditions are met. So the first condition is that all of your sequence terms are positive. So the greater than or equal to 0 means positive. And next, the terms are decreasing. So b sub n plus 1 must be less than or equal to b sub n, aka the next term in the sequence needs to be smaller than or equal to the previous term. That's for all n greater than or equal to 1, so for all terms in your sequence. Next condition, the terms have to have the limit 0. So the bn part of your sequence terms must be heading to 0. So you can disregard the alternating part when you compute the limit and compare the terms, but you need to have decreasing sequence terms headed toward 0 if you ignore the alternating part of the series. It's fairly straightforward. Let's take a look at a couple examples of applying this alternating series test. So our first example, we're going to determine whether the series converges, diverges, and for part A, we'll do the series -1 to the n plus 1 over n squared. Okay, so let's first check our criteria. So to apply the alternating series test, do we have all terms of b sub n, which is 1 over n squared? Are they satisfying our criteria? Is 0 less than or equal to 1 over n squared? Yes. Okay, n is always positive because n is greater than or equal to 1. So we're good for positive. Now we need to verify that our terms are decreasing and that the limit is 0. So next, 1 over n plus 1 squared is definitely going to be smaller than 1 over n squared because n plus 1 squared will be bigger than or equal to n squared for n greater than or equal to 1. Okay, how do I know that? The numerators are the same. The denominator of n plus 1 quantity squared will be a larger number than n squared because our n is always positive. So first condition of the inequality is satisfied. Next, we need to verify that the limit as n, so this is condition 1. Condition 2, the limit as n goes to infinity of 1 over n squared is going to be 0. Okay, so by the alternating series test, our series converges. Perfect. Let's take a look at a little more interesting example. We'll take a look at the series -1 to the n plus 1 times n over n plus 1. So first, verifying our condition, our b sub n is n over n plus 1, and we need to verify, 1, that the terms are positive. So that is satisfied trivially because n is greater than or equal to 1. Next, we need to verify that n plus 1 over n plus 1 plus 1, the next term in the sequence, it should in fact be smaller than our n over n plus 1. This ends up being n plus 1 over n plus 2, which is, let's see, n over n plus 2 plus 1 over n plus 2, which would be going to be bigger than n over n plus 2. So we'll keep the 1 over n plus 2 and compare that. And we want to compare that back to n over n plus 1. So n over n plus 1, the denominator has gotten bigger. So this, in fact, is getting smaller instead of bigger. N plus 2 is a smaller denominator, or n plus 2 is a bigger denominator than n plus 1, but the numerators are the same, so that means that the bigger denominator is going to make a smaller number. But hold on a second. Before we try and prove that this criteria is satisfied, I was looking at it saying, I'm not sure how we're going to verify the inequality that the terms are decreasing. What we can do is a graph might help us with that, but I noticed that our second condition isn't satisfied. So if we try and move on to, so we're not sure about the inequality yet, but I don't think it's going to matter, because if we try to compute the limit as n goes to infinity of n over n plus 1, that is the same as if we factor out an n from the numerator and denominator, leaving us with 1 over 1 plus 1 over n, which gives us the limit of 1, so not 0. So we can't conclude basically we can't apply our alternating series test. So it's okay if we didn't figure out criteria 1, because we already could tell that we didn't satisfy criteria 2. So instead, the divergence test, which when we take our limit as -1 to the n plus 1 times n over n plus 1, is going to give me a limit that is not 0. It's going to be alternating numbers approaching the value 1. So unfortunately, or I guess fortunately, if you're looking for a conclusion, instead the divergence test, having that limit not be equal to 0, implies our series diverges. Okay. So now let's take a look at these alternating series, a property that they have called the remainder. So a nice property of alternating series is that, let's say we're trying to find the remainder, which is how far off the sum is from your nth partial sum. So assume you have some alternating series, and we'll call the sum S, where our series satisfies the following criteria. We're going to let the S sub capital N denote the nth partial sum. And we will define R sub n to be the remainder, which is you take what the series converges to and you take the difference from the nth partial sum. The property that's really nice about these is that it turns out the remainder is less than or equal to the next term of the positive part of the sequence. So if we just look at the Bn part, the remainder is going to be less than or equal to B sub capital N plus 1, which means the next term of the B sub n sequence. So let's calculate the remainder estimate. Let's consider the alternating series -1 to the n plus 1 over n squared, and we're going to use the remainder estimate to determine a bound on the error of R sub 10. So we'll find the 10th remainder. Okay, so from our theorem above, R sub 10 must be less than or equal to B sub 11, which is equal to, let's see, our B sub 11 is equal to 1 over 11 squared. So I ignore the -1 to the n plus 1 part because that's alternating. The rest of the sequence is 1 over n squared. And then I plug in the 11, and that is 1 over 121, which is equal to, or I guess approximately, 0.008265 if we need a decimal formula. So our remainder will be less than or equal to 0.008265. Okay, so a common question that I get about remainders is why are we dealing with an inequality? Why can't we just say the remainder is and then find out exactly what the remainder is equal to? Which is a good question, but if you think about how infrequently we can actually conclude what a series converges to, you'll notice all of our series tests, the only ones we really know what a series converges to is like the geometric series. And very few other series can we actually figure out what exactly the sum is. So because of that fact, because we frequently don't know exactly what the limit of the series is, we can't say exactly what the remainder is. So the bound on the remainder just says, okay, at worst, it's this bad. So if you're trying to just approximate that, like you're trying to use series to approximate something that's important, you will just have to know, okay, we need to go this far out in our series to get enough accuracy, basically. So you just need a bound to get within a certain margin of error for whatever your problem is. And that is going to be intrinsic to whatever applications you're working on. So obviously, if you're looking at like designing parts for a plane and you're using these functions to approximate something, which we'll kind of see in future videos. If you're designing something like planes, I would imagine that's very high stakes and you want a very high degree of accuracy. Maybe some other applications you don't want or don't necessarily need as much accuracy. Okay, let's keep going. And next we'll talk about two different kinds of convergence. So we say that a series exhibits absolute convergence if when you take the absolute value, the series converges. We say that a series exhibits conditional convergence if when you look at the original series, it converges, but when you look at the absolute value of the series, it diverges. And let's say that you have established that your series absolutely converges. Then you can conclude your original series must have converged as well. So basically what you can't say is that because an original series converged, the absolute value of that series converged. You can't necessarily conclude that. They are not always going to have the same behavior as each other. So this is truly a one-sided statement, and you have to pay attention to the if and the then. It's not equivalence. Okay, let's work on these definitions on some examples. So for each of the following series, we're going to determine whether the series converges absolutely, conditionally, or is divergent. Okay, so our series that we're going to start with is -1 to the n plus 1 over 3n plus 1. And let's first take a look at what the absolute value would be. So the absolute value of our series is just 1 over 3n plus 1. So we'll be looking at the series 1 over 3n plus 1. And looking at this series, what is it going to be the most resembling? Well, I see the divergence test isn't going to conclude that it's divergent. I cautiously think that it's resembling the harmonic series if we just imagine the 3 and the plus 1 aren't there. So let's compare this to 1 over n using the limit comparison to the harmonic series. So if I take the limit as n goes to infinity of our unknown over our known, the harmonic series, we end up getting n in the numerator, 3n plus 1 in the denominator, and as n goes to infinity, we get, factoring out the n in the numerator and denominator, we're left with the limit as n goes to infinity of 1 over 3 plus 1 over n, which is just going to give us 1/3 for our limit. So if we think back to our limit comparison test, we've got a finite number, which means that the behavior of the series is the same. So by the limit comparison test, our series 1 over 3n plus 1 behaves the same as 1 over n. So it is divergent. Okay, so the absolute value of the series is divergent, which means that we do not have absolute convergence. Do we have conditional convergence? Okay, so no absolute convergence. Now we'll take a look at the original series. The original series is an alternating series, so it looks like, we'll see if we can apply the alternating series test. So if we take a look at our series terms, we need to verify the criteria. So we need to verify that the series is in fact decreasing. 1 over 3 to the n plus 1 plus 1. Well, the numerator is staying fixed, and the denominator appears to be getting larger. So it looks like our terms are definitely decreasing. And then all of them are positive, so that's satisfied. And then when we compute the limit as n goes to infinity of 1 over 3 to the n plus 1, we end up with 0. So by the alternating series test, our series -1 to the n plus 1, 1 over 3n plus 1 is convergent. Okay, because the absolute value of the series converged, but the absolute value version did not, this is conditional convergence, right? So let's look at the definition again. If the original converges, but the absolute diverges, we call it conditional convergence. And the conditional convergence is the condition being it depends on the alternating part. Okay, so we have conditional convergence, and that's pretty much all we need to establish. Let's take a look at one more to just practice that definition. For our next example, we'll look at cosine of n over n squared. And remember, what we need to establish is whether we can take the absolute value So computing the absolute value of n squared. We're looking to see whether this series converges, and it looks like we can compare this series to, doesn't look like an alternating series test lends itself well here, but I can see that this series is going to be related to 1 over n squared, because look, the top, you can just put the absolute value bars on the numerator because the bottom's always going to be positive anyway. And cosine of n is bounded below by -1 and above by 1. So because cosine of n lives between -1 and 1, the absolute value of cosine must be less than 1. So if the numerator is less and the denominator is the same, we have this inequality going on for us. So I see that we have all positive terms happening, and we have this inequality established, which means that we have, let's see, we know that this is a convergent p-series. So 1 over n squared is a convergent p-series because p is equal to 2. And we learned in our integral test video that p-series will converge when your power is greater than 1. So we have a convergent p-series, and then we have a series that's bounded by it. So that means by the comparison test, our series cosine of n over n squared converges. Okay, so we definitely have absolute convergence. Okay. And as a side note, remember that we have this cool theorem, which is that if our absolute value converges, then the original converges. So technically we weren't asked to come to that conclusion, but it's just nice to note what that theorem gives us. Okay. So this concludes our look at the the alternating series test. In future videos, we're going to jump into our ratio test and our root test, and then that will kind of complete all the tools we have for our series test, and I'll see you then.